Good morning, everyone. Um, I did send an email about the final exam, either Thursday or, Friday or Thursday. And I gave you the time. I asked you to reply to the same email. So please, you make sure you reply to the same email. Otherwise, I may lose your individual email. So one person contacted me using not using that email. So I'm gonna ask that person if he's listening to us today to resend it, to reply to the email I sent. All right. Any questions? Okay. I
Sure.
wanna
Oh,
Yes, please.
one on the test. How long do you expect it to take? Just
The exam.
approximately. Yes.
I would not. I will when you start on it. I will empty your schedule. Okay. So I don't expect it to take more than 3 4 hours.
Perfect. That's what I was looking for.
Yeah.
Um, and then I have a second question on the homework that you have assigned.
Go ahead.
Problem 7.6.
Let me take a look at it first.
Yep, go ahead.
7.6.
Correct.
Yeah. What's about it?
So my question is regarding the second part of it that says show that all solutions tend to the origin as t goes to infinity.
Right.
I am not sure, and also having talked to several other students, we are not sure how to show that based on what you've taught us so far.
Can you linearize it?
But
Well, I said you need to use either Lyapunov function and the linearization method.
um, I don't see 7.6 doesn't mention linearization.
Oh,
Uh,
7.6, 7.6.
yeah, sorry, exercise 7.6.
Okay, use the indicated function. So which one are you talking about?
I mean, all three of them. I'm not clear what we've what we know about Lyapunov functions that allow us to say that it goes to the origin as time goes to infinity.
Well, basically, um,
Like the
well,
first,
it depends what you get. Basically, did you find V prime?
yes,
Is
right.
it
So
negative? Is it negative or not?
yes, that part's easy to show that it's asymptotically stable for
Okay.
the three that you assigned. The question is saying that all solutions go to the origin. So the first one's simple because 0, 0 is the only equilibrium point. Well, then, of course, everything, if it's asymptotically stable, is going to go to it. But the second one has more than one equilibrium point. So
Second one. No,
part B should have more than one equilibrium point. And so
that's not
if
true. That is not true. B has one equilibrium point. No, the origin is on the only critical point. What's wrong?
I'm just thinking here. I didn't actually go through it, but it looked like it should have more than one.
Uh,
Um,
X prime equal to minus x plus 6y. Y prime is minus x minus 2y. So minus x minus 2y equals 0. Minus x equal 2y. X equal to minus 2y. Put it here. Then minus x plus 6y is 2y plus 6y equals 0. Y is 0, the only one.
yep.
Then x equal minus 2y, you get x equals 0. This is it.
So is it sufficient just to say, hey, it's asymptotically stable and it's only got one equilibrium point? Is that enough of a proof then to show
Yeah,
everything's going to go to the
yeah,
origin?
yeah, yeah.
Okay.
So let's take a look at v. V prime is 2x minus x plus 6y, right? And then I said a plus 4y, y prime minus x minus 2y. So This is minus 2x squared plus 12xy minus 4xy minus 8y squared. Okay? So that is minus 2x squared plus 8xy minus 8y squared, right? If I factor this out, this is minus, and let me factor 2, will be x squared minus 4xy and a plus 4y squared. So this is minus 2 times x minus 2y squared. Now look at the example I did in class. So v prime is all the set xy such that x equal to y. Remember that theorem?
Yes.
Okay. So you have x equal to y, right? Then, so this theorem tells you that if you are in the neighborhood of 0, 0, the solution will go to infinity. So let's take a look, x equal to y. Let's take a look here. Then x prime is minus x plus 6 times x over 2. That is 3x, right? 2x. Okay? And then y prime is minus x minus 2y minus 2y is minus 4y. So this has a solution, x equals c1 e to the 2t, and this is y equals c2 e to the minus 4t, correct? So you want x equal to y. That means c1 e to the 2t equal to c2 e to the minus 4t. This is if and only if c1 equals c2 equals 0. So that means the only bounded solution is the equilibrium point. So therefore, the xy go to 0, 0. Okay? Did you understand which theorem I'm talking about?
Yeah, I think it's 714.
Yeah, there we go. And I did a nice example, and you got almost similar Lyapunov function, okay? So you do your linearization, and then voila, it's asymptotically stable, and then you do Lyapunov function. So this question is mostly related to the second part, to the Lyapunov function, okay? No, not linearization. So this is what you should get in all the parts. You should get something like this with V prime. Okay? So you define this.
I guess I'm not clear. Either I'm missing something or the proof doesn't state it explicitly. How does that show that all solutions go to the equilibrium point to 0, 0?
Okay, read the statement of the theorem. Let's read it. Let V of x be a Lyapunov function in D. Let Z be the set x such that V prime of x equals 0x in D. Suppose that the only bounded solution of the system that remained inside D all the time is the equilibrium point. Then the origin of 7.11 is asymptotically stable. Basically, it goes to 0.
So, okay, because your set D is all real numbers.
Yeah,
that's how you're getting it for everything. I got it. I'm following now.
Set D is including in R2 where 0 is in D. Okay?
Makes sense.
And remember, the statement of the theorem says it very clearly. And so you will get what you're really asking for. It's a very neat theorem. Suppose that the only bounded solution that remain inside Z all the time is the equilibrium solution. So we showed C1 equals C2 equals 0. That means xt yt is 0, 0, right? This is the only bounded solution.
Yep.
You see that? All
And
right.
since it's the only bounded solution, it's asymptotically stable, and we're covering the whole domain of the real numbers. Everything's going to go to it. That makes sense.
Yeah, anytime. And this has no restriction on your initial point. Okay? As long as your set D contains 0. All right? Any other questions? I want to go back to example 7.11. The book is totally correct, but I missed something here for you. Example 7.11. So we have So we have 0, 0. We take v of xy equal x squared over 2 minus squared over 2. That is positive on u equal to the set of all xy in R2 such that x less than 1, y less than 1. Okay? All right. So now, and we did v prime, and we got 3x squared plus 2y squared plus xy squared minus x cubed y. And we said we wanted to compare this one. So we did. So you see xy squared minus x cubed y. This one is less than xy squared okay, xy squared minus x cubed y, which is xy times y minus x squared. So we're going to use a minus b squared is bigger than 0 and get ab less or equal to a squared over 2 plus b squared over 2. So this is less or equal to x squared over 2 plus y squared over 2 times y minus x squared. And this is 1/2 x squared plus y squared times y minus x squared. Okay. Again, no, I did not use this one. Well, I mean, last time, okay, so I don't want to go that far right away. So let us use, this is A, this is B. So this is less or equal to x squared y squared over 2 plus y minus x squared squared over 2. Okay. Okay. I believe, so now this is less or equal to x squared over 2 plus y minus x squared over 2. That is 1/2 x squared plus y minus x squared. Now, this is where we got into trouble yesterday. X squared plus y squared minus 2y x squared plus x4. And this is less or equal to 1/2 x squared plus y squared minus 2y x squared plus x squared. Because x4 is less than x squared. And so this is equal to 1/2 2x squared plus y squared minus 2xy. Now this 2x minus 2x squared y. Okay? Now this gave us trouble yesterday. So let me think. Go ahead and catch up. Should be in front of you, all of it, up to here. So I'm not going to change my set, and I will show you how to proceed with it. Okay? All right. So I'm going to flip the board, if you don't mind. So we have, you notice a plus b squared, 0 is less or equal to, which is a squared plus 2ab plus b squared. So this basically is bigger or equal to 0. So 2ab bigger than minus a squared plus b squared, correct? Minus 2ab is less than a squared plus b squared, or minus ab is less than a squared over 2 plus b squared. So we're going to use this inequality too. So v prime, so now this term I was looking at, xy squared minus x cubed y, is less or equal to xy squared minus x cubed y, less or equal to, remember we have 1/2 x squared plus 2x squared, 2x squared plus y squared minus 2x squared y. Now this is less or equal to 1/2 2x squared plus y squared. Now this one plus, let's use this one, minus ab, s squared plus b squared, x4 plus y squared. This is less or equal to 1/2 3x squared plus 2y squared, which is less than 3x squared plus 2y squared. There we go. Okay? So now your v prime is positive. Okay? So what do you have? You have, so you remember what v prime is. V prime was 3x squared plus 2y squared. And then it was plus xy squared minus x cubed y. And that is bigger than 3x squared plus 2y squared. And this one is bigger than this, plus 3x squared plus 2y squared, which is positive. Okay? There we go. Okay? Any questions? All right. Okay, now we're gonna go back to our now theorem, back to theorem 7.5. Please reread the theorem, okay? So you can do theorem 7.2. Then the condition is this holds if and only if A has negative real part for eigenvalue. It's the same theorem, but instead, so AT plus BA equal minus C. So remember our condition was ATB plus BA equal minus C. So let's take it here to be I. So we're gonna find ATB plus BA equal minus I. We're gonna take C to be I. Okay, and I'm gonna look at example 7.24. Find a strict Lyapunov function Lyapunov function to show the zero solution of x prime equal to -1, 0, 2 minus 3, x1, x2, for t positive is asymptotically stable. So basically, we need to find a positive definite matrix B, okay, so that ATB plus BA equal minus I. Then the Lyapunov function is xt xtbx. That would be the Lyapunov function. Okay. So the matrix B has this form: AB, BC. This is a 2 by 2 matrix. So that is symmetric. So this matrix is symmetric. Okay. All right, so this is what we need, ATB. So AT, what is A transpose? Minus 1, 0, 2 minus 3, will be minus 1, 0, 2 minus 3 times B, A, B, B, C, plus BA, AB, BC, times minus 1, 0, 2 minus 3, equal to minus 1, 0, 0, 1. Okay? So we need to find A, B, and C. If we find A, B, and C, we are done. Correct?
Can I ask a quick question about matrix C, the positive definite symmetric matrix C?
Right. What about it?
Is there a reason to do anything other than the identity matrix for it?
Yes, you get better result. If you go deep down into research, yes.
Okay.
Yeah. But for now, this is what we're going to have. Okay? So, and we showed that I is a positive definite yesterday, right? All right. So let's see. So this is our equation. All right. So what I have is minus 1, 2, 0, minus 3, AB, BC. What am I doing? Let's stop multiplying. Minus A plus 2B minus B plus 2C minus 3B minus 3C plus minus A plus 2B minus 3B minus B plus 2C and minus 3C equal minus 1, 0, 0, 1. So we have, add these together, minus 2A plus 4B minus 3B minus B minus 4B plus 2C minus B plus 2C minus 3B minus 4B plus 2C minus 6C equal minus 1, 0, 0, minus 1. And we see that C is immediately 1 over 6 from here. Okay? And I have minus 4B plus 2C equals 0. Minus 4B plus 2C from here or here, either one. So C is 2B, or may I say B, so minus 2B equals C, B is minus C over 2, that is minus 1 over 12, and I need A, minus 2A plus 4B, minus 2A plus 4B equal minus 1, minus 2A equal minus 1 minus 4B, 2A equal 1 plus 4B, 2a is 1. What is b, did we say? Minus 1 over 3. That is 2 over 3. Then a is 1/3. So I got all of them. Okay? A is C is 1 over 6. B is 1 over 12. I do have a sign problem somewhere. Let's see. We have a sign problem. Minus 4b plus 2c equals 0. Then, oh, here. We have a problem here. This is minus 2b equal minus c. So it's 1 over 12. And b is 1 over 12 plus 1 over 3rd will be 3 plus 1 will be 4/3. Then a is 2/3. All right. So that should match the book, correct? Okay, so the matrix B, we said it's A, 2/3, B, where is B? 1 over 12, B, 1 over 12, and C, 1 over 6. There. Okay? And now the Lyapunov function v of x1, x2 equal to x1, x2 times 2/3, 1 over 12, 1 over 12, 1 over 6 times x1, x2. Remember, x is x1, x2. So this is the transpose. And if you multiply this together, you will get you will get 2/3 x1 squared plus x1, x2 over 6 plus x2 squared over 12. You can keep it like that, or you can take something bigger than this. All right. So that Lyapunov function is positive definite. Okay. And in the book, I argue that this is bigger than 1 over 12 x1 plus x2 squared. Okay? All right. Any questions? Well, you can see that here 2/3 x1 squared is bigger than 1 over 12 x1 squared. That's what this is coming from. Okay. And then you can you can just play it out. And so this is bigger than, so if you want, this is bigger than 1 over 12 x1 squared plus x1 x2 over 6 plus x2 squared over 12. Okay. And then if you take 1 over 12 out, you get x1 squared plus 2 x1 x2 plus x2 squared. You see that? And that is 1 over 12 x1 plus x2 squared. Okay? That's how you show it's positive definite, but we already know through the matrix B it's positive definite. All right, I'm going to stop here for this and move on to another theorem. So by the way, I'll give you a few minutes to copy that, then I will elaborate on it. All right. So let's flip. Any questions? A symmetric 2 by 2 matrix B equal that is positive definite if A is positive, C is positive, and AC minus B squared is positive. Okay. Any questions? This is the last theorem I'm going to do for the course. I'm going to state it and do it now. And this is theorem 7.53. This is similar. Okay, you deserve, this is the last time. You deserve a better, darker ink. So let me get rid of it. All right. So now this is reconsidered. Before I state the theorem, okay, so let me do, So now we look. The perturbed nonlinear system x prime equal to a xt plus gt of xt. We have xt naught equal x naught, t bigger or equal to t naught bigger than 0. Let's call this is 7.5. Now we did this theorem for linearization, and it's really the same. Okay, so but we're gonna do it using layup on a function now. And so here x denote the Euclidean norm, and the metric cx is less or equal to c times x, or n by n matrix c. So this is the norm we're going to be using. All right. So here we have x is x1 to xn, and gtx is g1t x gntx. Okay, so this is the setup of the system. All right. So here is the theorem. Let me make sure this is the theorem label. 3, sorry. Okay. Suppose there exists a positive definite matrix B, a positive definite symmetric matrix B such that ATB plus BA equal negative R. 7.56, and the lim as x goes to 0 of GTX over x is equal to 0 uniformly for t in 0 to infinity. Okay. Then the 0 solution of 7.5.5 is uniformly asymptotically stable. Okay. So what is this condition? All this means all eigenvalues of A have negative real part. Okay, this is what it means, because we prove the theorem if and only if. Okay. Any questions? All right, let me go over the proof. I'm gonna keep the theorem here, keep everything. Just keep that in mind. Okay, 1 minute so you can copy it down. All right, so let's flip the board to do the proof. Okay, proof. Suppose the existence of the matrix B we define the Lyapunov function by V of x equal to xt dx. We know that this is a positive definite, right? Because of the characteristics of the matrix B, this is automatically is positive definite function. Then V prime of x equal xt prime bx plus xt dx prime. Xt prime, remember I am looking at x equal ax plus g. Okay, so that will be ax plus g transpose bx plus xt b ax plus g. Okay. Any questions? I think in the book, damn it, this X is missing in the book. All right. So you make a change of it. Oh boy. All right. So this is equal to xt at plus gt bx plus xt, okay, ba x plus g. So let's multiply them. That is xt at bx plus gt bx plus xt ba plus xt bax plus xt g. Okay. No, okay, again, xtbax, xt, oh, so this is wrong. Xtb this. So this is gonna be plus xtba x plus xtbg. Okay. Any questions? So let's take this term and this term. So this is equal to xt atb plus bax. So these two terms. All right. Plus, first of all, let's take a look at xt b g transpose. And this is gonna be bg transpose x. And this is a gt bt x. And this is a gt bx. So plus GTBX plus this is the same as XTBG transpose. So this is XT ATB plus BA X plus 2GT BX. Okay. All right, so this is xt minus I x plus 2GTDX. And that is minus x squared plus 2GT dx. Okay. And this is, and so v prime is less or equal to minus, this is the norm, plus 2 2xb g. Okay. I mean, look, guys, why could I have to take xtbg? Can anybody tell me why this one transpose is the same as this one? You have an idea? You should be questioning, why did I change this to this? That means if I interchange them, that means they are the same. Where they are the same. Remember your V is from the set D into 0, infinity. So V is a scalar. So this term is a scalar. This is a scalar number. The transpose of scalar number is the same. All right? Okay. Now we're going to use all right, so now let epsilon be positive. We may choose epsilon small enough so that condition 7.57 implies GTX less or equal to x over 2 for x less than epsilon. Because what is it? It is this condition here goes to 0. So we can always do that. Oh, I'm sorry. I wanted 2b. 2b GTX less or equal to x over 2. Hence, v prime of x is less or equal to minus x squared over 2 plus x times x over 2. Because I have x here. And this one is x over 2, which is equal to minus x squared over 2. Okay? Any questions? Okay, I'm gonna flip the board here. Since B is positive, definite, symmetric, we know that xtbx less or equal to alpha 1 x squared. Let me use the same notation. And alpha, I'm using alpha and beta squared x squared. Okay? So that means alpha x squared less or equal to vx less or equal to beta squared x squared. How's that? Then if I multiply by minus, minus alpha x squared divide by beta, or x squared less or equal to minus 1 over beta squared vx less or equal to minus alpha over beta squared x squared. Let's see if I'm using alpha squared. I am using alpha squared. So that's okay. And then here will be alpha squared. Okay. Any questions? If I divide by 2, that should be correct too. Okay. What does that mean? This one is v prime of x less or equal to minus 1 over 2 beta square v of x. There we go. Okay. Remember, this is v prime, isn't it? That is v prime. Less or equal to minus 2, minus 1 over 2 beta square vx. So we're going to work with this. That is the first order differential equation. That means v prime over v, let's say equal minus 1 over beta squared. So ln of v is minus 1 over 2 beta squared t, right? Okay. Then take exponential, v equal minus 1 over 2 beta squared e to the t. And times c, times some constant k, right? So what is k here? At t0, at x equals 0, we have x0 bx, okay? Okay, so we know that v of x0 equal to minus 1 over 2 beta squared e to the t naught k. So we have 2 beta squared vx naught equal k e to the t naught. So 2 beta squared vx naught over e to the t naught is k. Okay.
Wouldn't it be k times e to the negative 1 over 2 beta squared t instead of negative 1 over 2 beta squared e t k like you have?
Let's see. Thank you. That's a good catch. This is e to the minus 1 over 2 beta squared tk. Is that what you meant? Here.
Yes.
Okay, now let's apply t naught. This will be e to the minus 1 over 2 beta squared t naught k. Okay. And so k is e to the 1 over 2 beta squared t naught vx naught. So the solution v of x is this one, e to the minus 1 over 2 beta square t times Vx naught e to the 1 over 2 beta square t naught. Let's combine them together. Or V of x is less or equal to Vx naught e to the minus 1 over 2 beta square t minus t naught, and this is for t bigger or equal to t naught. Okay. All right. But what is V? V, okay, remember from this one, what is my alpha and beta? Okay, remember we have alpha squared x squared less or equal to V less or equal to beta squared x squared. So that means if I take these, alpha squared x squared less or equal to Vx naught times e to the 1 minus 1 minus e to the minus 2 beta squared t minus t naught. So this is alpha squared or x squared less or equal to Vx naught over alpha squared e to the minus 1 over 2 beta squared t minus t naught. Okay? Now, so this is x naught bx over alpha squared e to the minus 1 over 2 beta squared t minus t naught. Okay? So for epsilon positive, we're going to let delta equal to something so that with x0 less than epsilon, no, x0 less than delta implies x squared less or equal to is going to be delta times b, and this is x naught 2 times delta over alpha squared, okay? And this is less or equal to 0, correct? This one here is less or equal to 0. And that is delta squared b over alpha squared. So x is less than delta times b to the 1/2 over alpha squared over alpha. So if I take delta, I want this to be less than epsilon. So we're going to take delta to be alpha over b epsilon. So that will be less than epsilon. So we have uniform stability. Okay? So the zero solution is uniformly stable. I need to finish the proof showing it's uniformly asymptotically stable. We're almost there. We have a couple lines and to do. So there's a lot of work. I did this proof because you learn a lot from it. There's a lot of techniques in this proof. And this is the kind of I like to do for a student to really learn a few different things, how things are put together. I'm sure you'll never ever use it again, but hey, you saw it once. It's part of the course. All right. Any questions? So we need to finish uniform asymptotic stability. So let delta equal 1 from uniform stability. Then for x0 less than delta, we need to show x less than epsilon for t bigger or equal to t0 plus t of epsilon. All right. So what do we really need here? We're going to have to work with this one here. So as from here, we get x less or equal to delta squared b to the 1/2 over alpha e to the minus 1 over beta squared t of epsilon. Why? Because we're going to assume t minus t naught is bigger or equal to t epsilon. Okay? All right? So minus would be, so this will be true. And what do we want this to be? Less than epsilon? What? Well, so this means e to the minus 1 over beta squared t of epsilon less than epsilon alpha. Now, delta is 1 over beta to the 1/2 since delta is 1. And then take logarithm on both sides. Take ln, so you have minus t of epsilon over beta squared is less than epsilon alpha over b to the 1/2, or t of epsilon is bigger than minus, oh, this is ln. ln of okay, so T of epsilon bigger than minus beta square L and that should do it. So there is your T of epsilon. Okay. All right. So let's see. Any questions? Here, all right. This is the theorem, and this is what it says. And do you have any questions? Any questions? I think there is not a typo. I made a mistake. I did not xt. This should be minus 1/4. Sorry about that. Because this should be minus 1/4, and then t will be minus 4. Okay, will be 4 minus 4 beta squared. Should be that. I skipped this one here. The book is fine. All right, so this is a proof of the uniform asymptotic stability. I don't know if I had any there's a couple examples in the book I ask you to use. And I'm really done. Any questions? So this is it for material wise. I hope you learned a lot. And I need to find my book. If you have not replied to me about the final, please do. Let me see if there is any. All right, let's see if there's any. No messages. All right, I'm going to stop recording.